Imagine two probability maps of the same world. The blue map, P, is what actually happens. The magenta map, Q, is what your model believes will happen. KL divergence asks a sharp question: if reality follows P, how much extra surprise do we pay for using the model Q? Here is the key formula. dKL of P relative to Q equals the sum over outcomes x of P of x times log of P of x divided by Q of x. Read it slowly. The ratio P over Q compares reality's weight to the model's weight. The log turns that mismatch into an information cost. And multiplying by P means we average the cost over events that reality actually produces. So if P says an event is common, but Q says it is almost impossible, the penalty becomes large. The model keeps being shocked by something that happens all the time. But KL divergence has a twist: it is not symmetric. dKL of P relative to Q is usually not the same as dKL of Q relative to P. Missing a real possibility is different from assigning too much probability to a rare one. That is why KL is not a normal geometric distance. It is more like a directional bill for bad expectations. In machine learning, this idea hides inside cross-entropy. Cross-entropy equals the true entropy of the data plus the KL divergence from the data distribution to the model distribution. The entropy part is the unavoidable uncertainty. The KL part is the model's avoidable mistake. Training a probabilistic model often means pushing that avoidable mistake down. Adjust Q until its probability map shadows P. So KL divergence is a surprise meter. Not how far apart are two shapes, but how expensive is it when the model bets against reality? A good model does not predict every single event perfectly. It gives the real-world probabilities that make the next observation feel much less surprising.